Welcome. Let's talk about solubility today. We are going to be looking at an application of equilibrium that is solubility equilibrium. But before we get there, we need to talk about what it really means just to be soluble and what it means to be insoluble and how we can represent that in equations. And what we know about what's happening on the particle level. So let's start just with those definitions. Something that is soluble, and we're talking about soluble in water here, will dissolve in water and dissolve significantly in water. Not just a little bit, but actually, a large quantity will dissolve in water. Something that is insoluble will not dissolve in water. If you think about why this happens and you think back to first year chemistry, for things to dissolve in water, the particles have to be able to interact with the water molecules. Whereas if something is insoluble, those particles are more attracted to themselves than they are to the water. There are definite patterns as to which ionic compounds will dissolve in water and which ionic compounds will not. And this little solubility chart does a nice job of summarizing that. If you look at this chart, you will see that there are the cations, so the positively charged ions, that might be part of a ionic compound, and then there are the anions along the top. And to determine whether a particular ionic compound is going to dissolve, you just look for the intersection on this little chart between your anion and your cation. So perhaps you have calcium carbonate. Well, calcium's over here, and so I'm in this second row, and carbonate's right here. So calcium carbonate would be expected to be insoluble. On the other hand, what if you had sodium phosphate? Well, sodium's right here, and this says sodium and potassium. That's also the other group 1 cations. And so if I had sodium phosphate would be expected to be soluble. Couple of thoughts about this solubility chart. First, AP is not going to expect you to have this whole chart memorized. What they want you to know are the major rules. So you need to know that the group 1 cations and ammonium are going to be soluble. You also need to know that nitrates and acetates are going to be soluble. And then because it keeps showing up on AP tests, although it is not explicitly stated in the AP framework, I think you should know that silver chloride and lead chloride, that those are going to be insoluble. We can use that solubility chart to help us predict if I mix two chemicals together, am I going to see a precipitate form? So a precipitate is just an insoluble solid that separates from solution. And in the reaction I've written here, I took two aqueous solutions. So copper chloride and sodium hydroxide are both soluble in water, so you can make an aqueous solution out of them. But when you mix them, you get a solid forming, and that is your copper hydroxide, so this is your precipitate. You'll also form some sodium chloride. If you look, this is a double replacement reaction, and the precipitate reactions we're going to be talking about in this class are going to be double replacement reactions. So to decide whether a precipitate is going to form, you're going to predict the products of the double replacement reaction, and then you're going to use your solubility chart to decide whether they're both going to be soluble and so no precipitate will be formed, or if one will form an insoluble solid and a precipitate. So let's finish this one off. So here I've got potassium chloride reacting with silver nitrate, and that's going to form potassium nitrate and silver chloride. KNO3, potassium's a group 1 cation. Nitrate is, nitrate. Both of those are always soluble. So this is going to be an aqueous solution. Things that are soluble form aqueous solutions. Silver chloride, though, would land in the category that says soluble except for silver, so it's insoluble. And so this will be your solid, and this will form a precipitate. Let's take a closer look at what actually happened during that reaction. So before the reaction began, potassium chloride was aqueous and silver nitrate was aqueous. And when your ionic compounds dissolve, they're going to break into their ions, and those ions are what are being surrounded by the water. So really, what I had in my first solution was potassium ions and chloride ions, and then I had silver ions and nitrate ions. When I mixed them, for that split second, I had all the ions, but then pretty quickly, silver chloride precipitated out. The silver and the chloride ions are more attracted to one another than they are to the water. And so when this reaction is done, what I have is silver chloride as a solid at the bottom, while the potassium and nitrate ions stay in solution. So I can represent this reaction with pictures. I can represent it with our balanced chemical equation, but I can also represent it as what's called a complete ionic equation. So I'm showing all aqueous solutions as they're actually found, which is as individual ions. And the complete ionic equation has an advantage, is it really shows us what's really in solution. But you'll notice if you look at this, that the potassium ions and the nitrate ions really didn't change. They're the same before and they're the same after. And so we call those spectator ions, because while they're present in the solution, they're not actually changing in any way. They're just watching while the other reaction happens around them. And so the last way we could represent this process is as what's called a net ionic equation, where I don't write the spectator ions. They're on both sides of the equation. They would cancel out. I only write the portions of the chemicals that are actually involved in the reaction at hand. And the advantage to a net ionic equation is it's clean and it's neat. It shows us just the parts that are changing and allows us to really focus on the chemistry that's happening. So I'm going to do one final example. We're going to write an overall reaction equation, complete ionic and net ionic equation for the reaction between a sodium carbonate solution and a calcium chloride solution. That word solution indicates that we have an aqueous solution, and so I know what those state symbols are going to be. So there are my reactants. I'm going to do a double replacement reaction. Double check that my charges cancel, so Na is +1, Cl is -1, calcium is +2, carbonate's -2, so I don't need any subscripts. Balance this equation, and then I need to figure out states. Na is a group 1 cation, and so anything it's combined with will be aqueous. And if you go back and look at that solubility chart, calcium carbonate will be insoluble, and so that will form a precipitate. That is a solid. So there's my overall equation. The complete ionic equation, I'm going to break apart all of the aqueous solutions, but I don't break apart the solid. And do note, if you've got an Na2, that means when that dissolves, I'm going to have 2 sodium ions. So make sure you have the subscripts for things that are not polyatomic ions become coefficients. And then I'm going to go through and I am going to write my net ionic equation. So things that are on both the left and the right side are spectator ions and will not be included in the final equation. And so as I look here, you'll notice I just rearranged the order of the ions. It doesn't matter what order they're in. They're all just in the beaker. And I have my ions that are reacting to form the precipitate. Shortcut. If you know what your precipitate is going to be, your net ionic equation will simply be that solid precipitate broken down into its ions. Sometimes that can save you some time on the AP test. But ultimately, this is what's going on, and you need to understand where that net ionic equation comes from.